Hello and welcome to the 13th video in this series on random number generators, accompanying the book Random Number Generators Principles and Practices. And here we're covering SP800-90A DRBGs, which we know what a DRBG is. It's also called a PRNG, and SP800-90A is a NIST government specification, US government specification, that describes 3 different DRBGs. If you look at 90A on the internet to read about it, you'll find a lot of talk about the Julie CRDRBG, which was removed because it has a backdoor in it that was put there by the NSA, and then a lot of other stuff about how bad it is. Here we'll be doing a deep dive into the actual algorithms that remain, how they're generally secure but also unnecessarily complicated, and have a few issues, and how to compare them in terms of efficiency and security and things like that. Okay, so we last looked at PRNGs in general, what their model is, how they're defined. Here we have 3 DRNGs, Ctr DRBG, hash DRBG, and HMAC DRBG. Those are the 3 algorithms we'll be looking at. But first, let's look at where this stands in the in relationship with the other 2 SP800-90 specifications. So A was the first one to come out, and it used to be called just SP800-90, and then it got split into A, B, and C, but it wasn't really split. They added B and C. A was more or less the same, except it had those old bad algorithms in them. So it describes the Ctr DRBG, the hash DRBG, and the HMAC DRBG. That's its job, to define DRBGs. But it also describes the hash derivation function and the block cipher derivation function, which are conditioning algorithms or entropy extraction algorithms. And we've looked at SP800-90B before, which contains extraction algorithms, so that it covers entropy sources, online health tests, and conditioners. This bit, those 2 derivation functions, hash DF and block cipher DF, what the heck are they doing in 90A, which is supposed to be describing DRBGs instead of conditioners, and we'll get into that. Then 90B covers the entropy assessment, and 90C is basically how do you glue these 2 things together. And so it's interesting because it's backwards. It says first take a noise source and the online health test and conditioner from 90B, and after that attach the DRBG, and then you get to the output and do. And so the order of the specs really should be 90B is 90A and 90A is 90B. But that's how they did it, because SP800-90 is what turned into 90A and had been there before. Okay, so moving swiftly on, because we've got quite a few slides to get through. The Ctr DRBG. So CTR means counter mode. So there's what we have called counter mode is CTR mode, and in this we're using CTR mode to as an inner algorithm within the DRBG algorithm. And as it says here, it's quite sensible, but the use of the derivation function in it is just silly, and we'll see why. So taking a high-level view of the counter DRBG, we have with or without the derivation function. You can choose. If you have full entropy input data, you do not need to use the derivation function, so you can just use the counter DRBG. If you have partial entropy input data, you need to use the derivation function to give you full entropy input data, and then have the DRBG. But of course, we've looked at 90B before, which contains conditioners, and so you can precede the counter DRBG with a SP800-90B conditioner, and that'll give you the full entropy input data. Or you can just use this derivation function without using the 90B conditioner, and that's up to you. But the DF is there for historical reasons, because 90B didn't used to exist. And when they wrote 90B, they didn't pull the DF out of this spec, which they should have done. Okay, so first we'll look at BCC. This is an algorithm they define that's used by the next algorithm. by the derivation function. But if you look at it, it's exactly CBC MAC. And CBC MAC is one of the SP800-90B conditioners. So okay, fair enough. We've got a CBC MAC like thing. So then we look at the derivation function and what's going on here. Well, we make a string of data. So we've got this data field here. That's the input data from the entropy source, or your 90B source, and then you have but prepended you put the total length of data to be that you're providing here, and then the total length of data you're asking for at the output here. You stick an 8 on the end of that, and then you pad it out to a multiple of the block cipher block length with zeros. So now we've got some data and a whole bunch of other stuff, like 65 bytes plus some extra padding. And what this practically means is you're going to have an extra AES or an extra BCC call in order to deal with all that data, because it's going to be quantized to 128 bits, which is the block size of AES. Then the next thing they do is they say the key we're going to put into this CBC MAC that we're calling BCC for no good reason is 00010203 up to 1F. So that's enough for a 256-bit key. And you're going to take the leftmost bits, as many as you need. So if you're got 128 bits, your keys, you'll be using half of it. 192, you'll be using 3/4, or 256-bit keys, you'll use all of it. So anyway, then it says, well, you're going to want a certain amount of data out. Now, how much data? For a 256-bit key size in a Ctr DRBG, it's going to take 384 bits to seed it. So you're going to want 3 blocks of BCC, because CBC MAC produces an amount of data out that is equal to the size of the underlying block cipher, which for AES is always 128 bits. So you'll need 3 of them to make 384 bits. And we'll see a bit later why we need 384 bits. Okay, and then, but if you've got a 128-bit key, you only need 2 of them. If you've got 192, you still need 3 of them, because it's not a whole number of block sizes. So you're going to waste, let's see, 16 bytes. Okay, so that's the derivation function. And the idea of this is it will give you full entropy data by compressing the input entropy data. So if you had an SP800-90B CBC MAC conditioner, all you would be feeding into your CBC MAC algorithm is the data, is the non-deterministic data from your noise source. So, and that would meet the spec, and you'd be producing full entropy output. So you wouldn't be wasting your time doing cryptographic processing on these 0 entropy values, the 8s and the 0s and the length, the input length and the output length, which are generally going to be fixed values. So they contain no entropy. So I think this is why I think the block cipher DF is silly. Leave it to 90B, and it's got a much more sensible implementation of a conditioner in there. And then the key, they've just, like I've just said, it's key 128 is all the bytes in incrementing in order up to from 0 to F, and then for 192 from 0 to 18 hex, and then for a 256-bit key from 0 to 1F. Now, when you have a CBC MAC conditioner, there was a paper by Evgeny Dodis, a professor at New York University, which described why hash, HMAC, CBC MAC algorithms were good conditioner algorithms, why they would be secure. And the requirement they had for the key going into the Mac versions, which require a key, HMAC and CBC MAC, is that the key be independent from the noise source data, like statistically independent. And when you look at these numbers, it's an incrementing series of values. And if you were treating it little endian, it would be a decrementing series of values, right? So it's either going up or going down. And is that a good choice to be independent of a physical process? No, because a physical process might be increasing or decreasing. They go up and down, and then because voltages go up and down. So this is a really bad choice for a key, because it doesn't do a good job of being independent from what a noise source might kick out. So what you want is some other key. So what we use at Intel is we do what we call a nums value, a nothing up my sleeve value. So we take basically counter mode, which is where you take a counter going 1, 2, 3, 4, and you encrypt that to under some key in order to create a pseudorandom bit stream. And it's normally for encryption, where you're going to XOR that with some data. But here we're just using it to generate we're just taking the pseudorandom sequence coming out of it. So, and we're doing 2 blocks of this. So we're encrypting 1 and 2 under the key 0. So we're picking the first 3 digits, first 3 integers in order to do that, positive integers. And when you plug that into AES, this is the sequence you get out for your 256-bit key. So that is a pseudo-random sequence out of cryptographic algorithms, and so is almost certainly independent from some data that a physical process would generate. It's not going to generate a pseudo-random sequence like that, or at least not with, at least with fantastically low probability. So we'll look a bit further at the block cipher derivation function, and this is you've done your processing of your input data and generated some data. What it then says is do this as many times as required to get as much data out as you're asking for, and then truncate it at the end. So that's basically the same as what's going on here, but we're digging into this notion that you need to do as many blocks as is required. Okay, so now let's look at the Ctr DRBG. So now we're actually looking at a DRBG, which is what this spec is supposed to be describing. And it has 2 stages to generating random numbers. It's got what's called the generate function and the update function. And they always go in that order, generate, update, in the spec. But of course, since it goes generate, update, you can, in our normal DRBG model, where you have a state update and then an output function, which is equivalent to the generate, you can also always put the dividing line in front of the update, so it's update, generate. Okay, so generate is you've got a vector, which is a 128-bit value. You've got a key, which is a 128, 192, or 256-bit value, and you might have additional input, and I'll have a little rant later about additional input and why you don't want it. But anyway, so this is your main state variable, v and k, and you increment v and then encrypt v to give you an output. And then to do the update, you increment v and you encrypt it to get some output, and again and again. And here the example is for a 256-bit keyed DRBG. So we're doing 2 blocks of this in order to get 256 bits of pseudorandom data, and then again to get another 128 bits, and we XOR those values with the existing value of the key and the vector v. So we've taken now if we were just to not to do the update, we would you'd see that wasn't a fully secure construct. Doing the update does is give you backtracking resistance, and it makes the probability of collisions the same as you would expect in uniform random data, and we'll look at that in a little bit later. The Ctr DRBG update, this is the function which it's the same as the last 3 of these of this generate update process, but they define the update algorithm separately because it's used for reseeding So this is just saying now, instead of additional input, it's saying provided data, because we have different uses for that. And let's look here at the sequences you end up with. So here I'm using the word generate as the whole process of generate update, because when you call generate, it does, the SP800-90A is a bit unclear about the domain of the term generate, but you call generate in order for it to give you a number. Then after it's given you the number, it does the update to refresh the key and vector. So you end up doing generate update for each time you a generate update cycle for each time you produce a number. But periodically you're going to want to do a reseed, and reseed wastes an update. So a reseed is an update where the provided data input is some fresh entropy, so that you're updating K and V with 256 bits or 384 bits of full entropy. And what that does is it breaks the algorithmic connection between what went before and what comes after. And so it's generally a security measure, because now you can't look at some string of data and do a bunch of mathematics on it and break it and find the key and the internal state and then follow it forward indefinitely, because the reseed acts as a barrier. But you've done a generate, and you said, right, I've done enough generates on the same key. I'm going to do on the same seed data, I'm going to do a reseed. But you have to do the update as part of the generate, and then you have to do the update again as part of the reseed, which basically wipes out the update you've just done. So there's this wasteful sequence of reseeding after producing some data. You update twice, and the first one is kind of pointless. There's also a thing called oversampling mode, which is defined in SP800-90C, and that says one way to achieve getting full entropy output from an RNG, rather than just computational prediction resistance of the type you'd get from a DRBG or a PRNG, is one way of doing it is oversampling, and that's the name they give it. And what they say is just generate some data and do a reseed, generate data, do a reseed. Put a reseed between each generate. So that invokes the bit of waste every time. You're basically doing generate update, generate update, where the second update gets the fresh entropy data. It's completely unnecessary. You don't need that. So it would have been more sensible if the specification had said you can generate data, and if the next thing you're doing is a reseed, just do the reseed. Don't do the following update that comes built into the generate, so that you're not wasting any time or entropy. Okay, so let's look at the reseed and initialize, and I just left them to the end here because they're pretty simple. They are calling the update function with where the input length is the length of K and the length of V. So it's saying I need full entropy data that is as long as my key plus as long as my vector, which for a 256-bit DRBG is 384 bits. For a 128-bit DRBG is 256 bits. Initialize is calling reseed, so it's the same thing. So that's I guess reseed does actually set the K and V values to 0 and then calls update to do something to it, rather than reseed, which takes the existing value and updates it. So when we think about the standard PRNG structure, a next state followed by an output function that we looked at in the previous talk, here we're looking at K prime, or the next key is AES-K of V plus 2, appended to AES-K of V plus 3, because you need to do two AESs because it's a 256-bit key, one if it's a 128, 2 and chop off 128 bits if it's a chop off 64 bits if it's a 192-bit DRBG. And then for V, take AES k of v plus 4. And the reason is this was preceded by the reason this starts at 2 is because we proceeded with the output function, but in our normal model the output function comes afterwards. So now the output function is the AES of the new, using the new key and the new vector, and you add 1 and then add 2, 3, and 4 for the generation of for the update that follows to generate the new key and the new vector. So that's pretty straightforward. So let's go back and look at the DF, because I'm trying to drive this home of don't use the DF, it's stupid. We have a noise source, and we're doing our design with the DF that comes along with the Ctr DRBG. And then that's going to give you your full entropy data, and you're going to put it into the Ctr DRBG, which will give you uniform cryptographically secure data at the output. You're going to need something like 8 to 18 CBC max over the noise source data, and doing that computation over unnecessary values, the length values, the 64 bits of length values, the added 0x08, and the padding, the zero padding. And then with a key which is inappropriate for the security model. If you were to use SP800-90B instead in the CBC conditioner, CBC MAC conditioner, you'd have your noise source, then you'd have 6 to 12 CBC max. And why would you have fewer of those? This is the equivalent number you would need for the same extraction ratio. So here I'm assuming a 256-bit DRBG. Basically any new DRBG today is going to be 256 bits, because nobody does 192, because that's just silly. Because you end up using the same resources as you would for 256 bits, so you may as well use 256 bits. And you're going to need 3 blocks of 128 bits of full entropy data to reseed it. And if you've got a 2-to-1 extraction ratio, you can't have a 1-to-1 because you're not going to extract any information. You need at least a 2-to-1 extraction ratio. So 2 times 3 is 6 blocks. And then but 2-to-1 is the minimum. Maybe you're going to go up to a 4-to-1, which is probably you could go higher, but for a normal, reasonably performing noise source, that would be sufficient. So 6 to 12. So you're doing 8 to 18 with the derivation function, because you're also computing over that extra non-entropic data, which adds no benefit. So use 90B conditioners, don't use the derivation function. It was left in there from a time before 90B existed. Okay, so what's the idea here? If you have a counter mode where you're taking incrementing values and you're encrypting them under the same key, what you get out looks indistinguishable from random, provided you have a sufficiently small amount of data. And why is that? Well, that's because for any 2 values which are different going into this AES, you're going to get different values out. Guaranteed. It's not this pseudo-random thing where it might give you the same value or not with some low probability. It's going to be different because an AES with it under a key is a bijective mapping. It's a 1-to-1 mapping of input to output. And so you change the input, you are changing the output. So for all NM where n doesn't equal m, AES of n doesn't equal the AES of m. So what happens is when you're looking at uniform random data and you chop it into blocks of a certain size, you have a collision probability which says if this is uniform random data, I would expect to see, say, adjacent pairs to have a probability of being the same, of being 1 in 2 to the power 128, because they're 128-bit values. What's the chance of the next one being exactly the same as the previous one? However, if you take a larger amount of data and say, how many collisions do I expect to see in this data? How many times do I expect to see any 2 values the same within a larger block of data? That then falls into what's called the birthday collision bound, in which the probability of seeing a collision goes up quite fast with the size of the data that you're looking at. And if you end up looking at 2 to the power 64 outputs from a counter mode and you don't see any collisions by then, you've got a very good idea that this is a way of distinguishing it from uniform random data, where you would have seen that, where you should have seen collisions by then. And so with counter mode, the probability of AES-KN equals AES-KM is 0 for N and M are different, whereas for normal uniform data, the probability of AES of K under an N with a different K and a different N is 2 to the power minus 128, because there's a different random mapping, because the random mapping, the bijective mapping, changes with each key. The key is just selecting between a set of random maps. So the idea of the Ctr DRBG is the key update, where it's running the CTR mode to generate both the output and data to mix in with the key and the vector to give you a new key and vector, so that you have the same collision probability as you would get in normal uniform data. So summarizing this counter DRBG, it's the most efficient of the three, and we'll see that partly because AES is a heck of a lot more efficient than SHA or HMAC-SHA. Either SHA-1, SHA-2, SHA-3, it doesn't matter. They're all they all take more computational effort to compute than AES does. Also, you have better support in CPUs for hardware for instruction level execution of AES. Intel and AMD chips have the AES instructions. There are some support for hashes, but it's more generic. So obviously it's based on a block cipher, AES. And one benefit of this is it's not a horrific mess like the hash DRBG, which is the next one we're going to look at. And keep that in mind. If you're trying to make a decision between what DRNG are we going to use, what DRBG are we going to use, you'd like it to be simple and efficient, probably. And when you look at all three, the Ctr DRBG is certainly the most simple and efficient. And so it's a logical choice to use. Intel's chips use the Ctr DRBG, and that was me that chose to use that. And this was a time before the Snowden revelations, when the Julie C DRBG was still in the spec. And I looked at them, it's like, well, the Julie C DRBG is clearly stupid and probably insecure. And boy, was I right about that. And then the hash DRBG and HMAC DRBG were, one, complicated, and two, a lot slower than the Ctr DRBG. And the speed matters, because, you know, your chip is providing random numbers to things which sometimes want random numbers at a high rate, like per packet nonces and things like that. But when you do use the Ctr DRBG, don't use the derivation function. The spec lets you not use the derivation function if you have full entropy data, and you have full entropy data because you're using the much more sensible CBC MAC conditioner from the 90B spec, not the derivation function from the 90A spec. Okay, next is the hash DRBG. So, subtitle, Be Afraid, Very Afraid. We'll see why. So, this comes with its own derivation function, but it is not optional. So, first question, why is it not optional? I don't know. But anyway, look at this structure. It's a bit weird. We're taking our input string of data from a noise source, and we're tacking some data on a fixed, this is the same value on all three of these. And what we're doing is we're doing it as many times as required to generate the number of bits we require, which is the number of bits we need to feed the next stage of the algorithm. And 3 is typically going to be the right amount. So you've asked for the number of bits, and you've told it the number of bits, and so on the last stage it will truncate the correct number of bits to give you the correct number of output bits you need to feed the next stage of the algorithm. And then you've got a counter, 1, 2, 3. But again, the input string is the same for each of these. So basically you are hashing 3 numbers which are the same only by, in this case, a maximum of 2 bits. And That seems a bit odd. If I was just hashing 1/3 of the input string and then hashing the next third and hashing the next third, it was all random data, all non-deterministic data, that would seem fine to me. You'd be doing less hashing overall, but all the input data would have entropy, unlike this where you're putting, again, 0 entropy data in and doing computation over it. I don't see the point. Now, I do understand why you might want that in some scenarios. This does a thing of putting, for instance, putting the number of bits in and hashing it makes you or resistant to things like extension attacks, where somebody says, I know what your hash is. I can take the output of your hash and compute what would have been the output had you had some extra data on the end of your input string. But if you're putting in the number of bits and something at the other end is checking that the number of bits is correct, then they're going to recompute it with the number of bits, and so basically the computation with the number of bits that includes the amount of data you have is going to be different to the computation for the number of bits for the amount of data you should have had, and so it resists extension attacks. But that's not what's happening here. This is not a situation where the adversary has some control of the input. The adversary doesn't have control of the input. This is a random number generator where you have your own noise source, and then this output is going into the next stage of the algorithm. So this isn't some service where the customer comes along and puts the data in the input and then gets the data at the output, or sends the output to somebody else. These are internal stages in a sequence of processing. So putting this kind of defense against attacks which don't apply seems silly and wasteful. So now we're looking at the hash DRBG instantiate. Each of the DRBGs has an instantiate, a reseed, and a generate function, where the generate encapsulates both the next state calculation and the output function. So this is defined as having some entropy input, which is the stuff coming from the noise source, but you can also throw in an optional nonce and an optional personalization string. So here we go, and you tell it the seed length you want, and then so we're going to instantiate the DRBG, and we're going to set the initial value of the vector and C, which stands for a constant. Right, this is a hash. There's no key, so we don't have a K. But we call hash df twice, so a bunch of hashes. And the first one, we're taking all this input data and hashing it down to something, and putting that in V. C, again, it stands for constant. This is going to remain the same until we reseed. But you take what you computed for V, put that here, tack a 0 on the front of it, and that becomes C, which is again a bit weird. Why not just take enough entropy input that you can initialize C and V from full entropy data? That seems more sensible, but they're doing this complicated thing instead, and you set the reseed counter to 1. In all the specs, I don't really go into that here, but there's text in the spec which says if your reseed counter reaches some reseed limit, then you can't produce any more data out until you've reseeded. In Intel chips, we have the reseed counter max as 511, and the reason it's not bigger is because we'll never get there. We have a fast entropy source. We are conditioning at around 500,000 seeds per second and reseeding that frequently. So the DRBG never gets to produce 511 values in between a reseed. So there's no point making the counter bigger. So that's why it's that size. It's big enough that we're never going to reach it. Okay, so hash DRBG instantiate. What does that? What does this look like? We call the update function and put all this data in, and v and k, and there you go. All right. The reseed function is where we're taking the hash derivation function. We've got new fresh entropy input data, and now we start tacking on arbitrary bytes. So they've tacked on a 1 here, put in v, put in your entropy input, and then it says, oh, any additional input, which could be none, or some. You could add some additional input. And again, I say, well, why? Why not just reseed with that additional input? Okay, and then compute C the same way we did last time. And because we're reseeding, we're going to reset the reseed counter to 1. Unrolling that reseed, what does that mean? Well, for a typical situation, it's going to be 3 hashes for this, and then 3 hashes for the computation of the constant. So 6 hashes to achieve what in a normal situation might require 3 hashes just over the entropy input. So very, very wasteful. Okay, the generate function. So we got two stages here. The first part is the update, which is a little odd. Actually, no, sorry. It includes an update, but this generates the output bits. So if you have additional input, you are going to stick a 2 in front of it, stick your old v into it, tack on the additional input, hash all that to get a value, and add it. This is a numerical add modulo the seed length. So that's a bit odd because we're used to, in cryptographic algorithms, addition being the XOR operation because we're operating within a Galois field, a binary Galois field. This is not this. This is numeric addition like you did at school. So that's a problem because it's slow. XOR is just a parallel operation, one gate deep. This is not that. You've got a carry to deal with. And then that value goes here to this v here. So this is a different v to this v, but that's what it calls it in the spec. But then you take this value, you stick a 3 in the front of it, hash it, and get another value. So these two values, they are algorithmically connected. This is a direct function of this by tacking a 3 on and hashing it. And then C is the value which is not changing from now on until we reseed, and then you have the reseed counter. And again, we're doing a numeric add of these 4 things modulo the seed length, and that becomes the new V. The C doesn't change, and the reseed counter increments by 1 because we've generated a number. This value we got for the for the intermediate value of V in this computation goes through hash gen, which is we'll look at, and to generate the output bits. And so here we are with hash gen, which is counter mode hash. Now, counter mode is usually associated with a block cipher, and that's how counter mode is defined. But there's no reason why you can't do a counter mode with a hash function too. And in the next talk, we'll talk about cha-cha-cha, which is a counter mode hash. Here and now, this W here is this W here. So if you have additional input data, you're going to add in the W. If you don't have it, you're just going to take V straight in, hash it to get some output bits, add 1 to it, hash it, get some output bits until you've got enough. And the last block, if it doesn't align, you're going to truncate it to the requested length of bits. So that's the hash gen. Trying to map this to the standard PRNG structure. So we've got some intermediate values here because it gets a bit complicated because it's a bit complicated. W is the H, big H is for hash. Hash of 2 prepended to V prepended to additional input. Temporary is V plus W. H is hash of 3 prepended to temp. And then the intermediate V is the temp plus H plus C plus RC. The C remains the same in increment RC. That's the next function. And the output function is hash of V plus W plus 1, hash of V plus W plus 2, until you've got enough output. Now, one of the reasons, if you're designing a DRBG, one of the good things to do is to say, does this algorithm make sense in this block, and does this algorithm make sense in this block? And you can see how, well, this one kind of makes sense. It's a counter mode hash. This one, why? Why is it like that? Do you not trust your hash function to be a one-way function? And if you don't, why don't you? And shouldn't you do something else to fix that than come up with this arcane construction? But that's what they did. Okay, so finishing up with the hash DRBG, it's unnecessarily complicated. It's based on a hash function, so SHA-256, 384, 512, or SHA-3. It's probably the least good choice for a NIST RNG that needs to be fast and secure, because it's slow and might be insecure. Why do I think it might be insecure? I don't really think it's insecure. I just think it's not doing a good thing. Particularly here, where the thing that's supposed to be creating full entropy data is actually creating data which is algorithmically connected. These 3 different output bits that you'd expect to be full entropy because it's a derivation function have only 1 bit changed in their let's say between the 2 and the 3. There's 1 bit changed. There's 2 bits changing between the 1 and the 2, out of a whole string of several hundred bits, right? So this doesn't seem to fit the definition of full entropy, and I don't understand why they did it like that. And this is a reason I would recommend against using the hash DRBG. You have to use the hash derivation function, and it's stupid. All right, rant over. Let's go on to the HMAC DRBG. So this one is better from a security standpoint of doing, it's not doing so much silly stuff, but we'll see it's not completely free of it. But this also makes it slower. If you're looking for a computationally efficient one, you're going to go for the Ctr DRBG. If you don't care, which you might not, then HMAC is a reasonable choice, but still has some balmy duplication of effort. All right, so let's start looking at its functions. We'll start off again with the update function, because they're using the update function for instantiation and reseeding and DRB and generating. Oh, look, it just got complicated. So it starts off saying, if you do these top 2 HMACs, so you've got K and V and reseed counter, and I haven't drawn in the lines for reseed counter. It's going to be set to 1 if you're reseeding. It's going to be incremented if you're generating, but that's not happening inside this update. Okay, so you take V, you tack on a 0, and you tack on the provided data, which you may or may not have. You may not be providing data. This might be the update done in a generate where you're not providing any more data, or you might be as additional input, which becomes the provided data. So either way, you tack on a 0, and then you tack on this extra data if you have any. HMAC the thing under the key, and the output of that becomes a new key, and then you HMAC V on its own under the key, and that becomes the new V. So if you don't have any provided data, the difference between this key and this V is that we are hmacking V plus with a 0 tacked on the end, and here we're hmacking V without a 0 tacked on the end. So again, it's kind of strange design decision of basically throwing in the same data with a small change to generate two values which we would like to be very independent of each other, but they are algorithmically connected in that the input data only changes with a few bits. At most, well, 8 bits. Exactly 8 bits. Okay. So then it goes on to say, if you did have provided data, do this next stage. So if you didn't give it any provided data, you're done. You've got your new K and V, the top side, new state. But if you did have some provided data, chuck away that new state, we're carrying on, and you do it again. You take the V that you computed, instead of putting a 0 on it, you're going to put a 1 on it, a single byte of 1. Again, give it the provided data, the same provided data you gave it here, and generate a key by hmacking that. Take key, put it in, hmac the key, and get the vector out. So, okay, that's all a bit weird. Well, it's doing the same thing they did in the hash, where they're saying, oh, let's take a value and we're going to process it twice with a small difference between them, when you could have just had enough state that you could separately process them, and they wouldn't interact with each other. So a bit disappointing in that design decision. Okay, hmac DRBG instantiate. So now we are starting it up. Personalization string. I'm trying to look at that spelling, not this spelling. So personalization string, entropy input, and a nonce. These are the 3 inputs you're allowed. And so you take the entropy input, which is what contains all the entropy, and tack on this other useless stuff. And that becomes your seed material. So you push this into hmac update with your previous key and value, but since we're instantiating it, we say set key to all 0s and V to all 1s for as many bytes as you have in your vector. And then that gives you a new key and a new vector, which becomes a new state, and we set the reseed counter to 1 because we're instantiating. Reseed is similar, and the diagram's wrong. Oh dear. Okay. Forget this stuff. Reseed is the existing K and V, and the seed material is the it was the additional input that you've given it, and a fixed string. That's what it is. Okay. So now on to generate, the last of them. So if we have some additional input, do this whole screen. We only do if we have additional input. Now this is good. This is one of the many reasons not to have additional input, but we'll get to that. And so you take your V and K and you produce a new V and K, which is an intermediate V and K in this generate process. And then you do this, regardless of whether you had additional input or not. So you take the V and K, which was either the V and K you started with or the V and K you got because you had additional input. So, so that's where we are here. And then we do a chain of hmacs. So we hmac V under K, and that becomes some output data. But we also hmac that data to get some more output data, and we hmac it again. And on the last block, you truncate it to match the number of bits you asked for. Now, if you're designing, say, a hardware system or a software system, when you're requesting a number of bits, this truncation business, generally you're going to design around it by saying you can only ask for 128 bits or 64 bits or whatever. That's how many we're giving you. The read seed instructions in Intel CPUs, they produce 64 bits. It doesn't matter how many you're asking for. If you ask for 16 or 32 by setting the target register, or 64, it doesn't matter. It's getting 64 bits from the RNG, and that's from a FIFO, which is actually getting 128 bits at a time from the RNG. So it's chopped down to 64 because that's the size of the instruction target register. So the point is, what we said is the output value you can get is exactly the output size of the AES, and then you don't have to be doing multiple blocks and truncation. So that's what you'd want to do here if you were designing a HMAC DRBG. And then finally, after you've finished doing all that and you've generated your output data, you're going to do another update, and the additional input we saw at the start. If you have additional input, you're going to give it here, and then you're going to get K and V, and you're going to increment the Reseed counter. So you're going to use if you have the additional input, you're going to use it twice, which is a bit odd, but there you go. So now mapping this one to the standard PRNG structure is a bit odd, because the next state function is a function of how much data you asked for. If you asked for a lot of data, you're going to run multiple HMACs, and if we go back and look at this, you have V, then you have a new V, then you have a new V, then you have a new V, and each of the V's we generate, the intermediate V's, is going to lead to some output data. So the output function is HMAC K and V, where V is the sequence of V's in the next state function. So if I ask for a kilobyte of data, I'm going to have a whole bunch of HMACs going on in the generation, and that is going to change the final state of V. So the next state of V. So the next state of V is not independent of what the requester is doing, and that's a bit suspect. So if there was a reason not to use the HMAC, and I'm not saying don't use the HMAC DRBG, I think it's probably fine. I can't really see how this is a backdoor or anything, but boy, that's weird. Why are they doing that? You would like the output function to take something from the state between, the next state you've generated, but not influence it. You want the output function to just be not revealing what the internal state is by being a one-way function. And so this is changing the normal relationship between a PRNG next state function and output function. And NIST are not to be commended for doing this. All right, so summarizing, it's probably got the highest security margin, because look at all those HMACs, right? There's a lot of HMACs are intrinsically more secure than SHAs. Example I can give you is SHA-1, which is deprecated because it's insecure. You can find collisions in a computationally efficient way. If you use SHA-1 within a HMAC, it doesn't suffer from the same problems, because what HMAC does masks all those problems. Now, this isn't an excuse to use HMAC SHA-1. Use HMAC with a good SHA, but HMAC itself, it does add a layer of security margin over a bare hash algorithm. But it uses way too many of them. As we saw, you're probably going to be using at least 6 and probably more. And thinking out this, well, how would I have done this? And I would have used a single HKDF. What's that? That's a HMAC-based key derivation function. So it's an algorithm. You can look it up. And being a key derivation function, you get to say how many output bits you want. So it's going to be and it's going to call HMAC inside it, and then generate a bunch of bits from that. And so you're going to have the output data you want, your new value for K and your new value for V. Take the length of all of those, and that will be the number of bits you're asking for. and then what you pass into HKDF is your old K and your old V. There you go. That's that's a construct which is as secure as the HMAC DRBG, but in one line, right, to describe the basic algorithm. You'd have to add the instantiate and the reseed, but that would be the reseed would be putting in fresh entropy into the K and V fields instead of K and V, and let's see, instantiate would be setting K and V to something and then calling reseed. So there's basically you can do this in better ways by using the right algorithm, and I don't think they're doing it the right way here. So looking back at the whole of SP800-90A, I'll start by saying this was not generated from a blank sheet of paper. What preceded SP800-90A was X982, which is still a standard. And the X9 series are the cryptographic standards that are used by the banking industry, although they're shifting to SP800 for various things, including the RNGs. And basically the same people who wrote X982 wrote SP800-90A, they just updated it a bit. And so all the stuff in SP800-90C and the stuff in some of the stuff in SP800-90B and the stuff in SP800-90A are somewhere in X982. It's just been updated. So this is not new design. This is from an earlier description of pretty much the same stuff. So the spec needs to ditch the personalization strings, the additional input, and the nonces. Why do they need to do that? One, it's wasteful. Those things don't contain entropy, and your job as a RNG is to take entropy from somewhere and turn it into cryptographically secure uniform random data. And putting in extra values doesn't help, and it can make things worse because the adversary might be the one doing this. Imagine the read round instruction on Intel CPUs, if that used an additional input or a personalization string. So before you called the read rand instruction, you had to call the set personalization string instruction. You could then read another paper by Evgeny Dodis at New York University on how you can structure input data to an RNG in order to cancel out the entropy that's being used. That may or may not be possible with these structures. I haven't looked. What he proved was it was possible with the Linux RNG, which is way worse than this. So don't even think of using the Linux RNG, but Linux kernel RNG. This spec would be simpler and better without all this other stuff. They're saying, hey, come on and inject your own data into the state of this RNG. Don't. That's just asking for trouble. And it's optional. So when you design an RNG, don't allow it. It's stupid and probably reduces security and certainly doesn't add to it. All three of them waste compute power. They have Ctr DRBG has wasted cycles, so wasted updates. The hash DRBG just has way too many invocations of the hash. The HMAC DRBG has way too many invocations of the HMAC, and they could get away with far fewer. And as I say, for the HMAC DRBG, the right kind of structure is a HKDF structure. For the Ctr DRBG, the right thing to do is to cut out the unneeded updates that come before a reseed. For the hash DRBG, just throw it in the bin. But of these, in terms of compute power, the Ctr DRBG is the clear winner in terms of efficiency, and that's why you'll find it's used in CPUs as their default thing they'll do in hardware. If you're a hardware designer, you look at this and you say, "Oh, I'll use the Ctr DRBG." That's the most easily implemented as well. The derivation functions have no place in the specification. It's not a conditional specification, it's a DRBG specification. You knew you were writing 90B because you'd already written it once in X982. you should have known that when you were as soon as you publish 90b, you need to publish an update to 90a, which gets rid of the derivation functions, and they didn't. And then the derivation functions themselves are unnecessarily complicated. Why is CBC Mac over entropic data good enough for 90b, but in 90a you need to mix in all this extra stuff? I don't know. It doesn't make any sense. But obviously, as a designer who's trying to make a compliant RNG to these specifications, you're not going to do the derivation function for the Ctr DRBG. You're going to take the Ctr DRBG without the DF and do the 90b one because it makes more sense. So a little backstory there is when the 90b draft came out with its conditioners, the first drafts didn't include the CBC Mac conditioner. But the Intel DRBG already, or DRNG, already existed. It was in Ivy Bridge long before 90b was a spec. And we put in CBC Mac. So it was a colleague of mine, as a mathematician, who said we should use CBC Mac because this paper, again by Evgeny Dodis at New York University, explains why CBC Mac is a good conditioner. So we chose to use CBC Mac, and it fit nicely with the Ctr DRBG because it's using AES as well. So we could share an AES unit to do all these jobs. So then we made comments against 90b saying, put CBC Mac in because every Intel chip contains CBC Mac as a conditioner. Oh, and by the way, here's the paper that proves it's a good extractor. And they did. So, because there's a comment period, you can make these comments. So we have this interesting situation where that we have had Intel silicon that has been SP800-90 certified, algorithm certified, against SP800-90A and SP800-90B, even though that silicon was designed and built before SP800-90B existed as a standard, which is a clever trick, right? But it's because we changed the standard to match the silicon and not the other way around. And then the last point is the hash and HMAC DRBGs. One benefit of them relative to the Ctr DRBG is it's more tolerant of data of arbitrary length. Hashes and HMACs take in arbitrary length data. Now you have a minimum amount of data you have to feed into it because you can't feed in 1 byte and get more than 8 bits of entropy, right? You need to give it enough data to do a reseed or to do an instantiate. But you can do enough data plus 1 byte, enough data plus 2, plus any amount of extra data. And so the Ctr DRBG says if I'm a 128-bit DRBG, I need 256 bits and only 256 bits of full entropy data for my reseeding. And if I'm a 256-bit DRBG, I need 384 bits of full entropy data to do a reseed. The HMAC and hash DRBGs, as I know, just give us enough and any extra you feel like. So there are specifications out there like FIDO, which have chosen to use the HMAC DRBG, not because it's better in any other way, but specifically because they're working in some constrained environments and they don't have a lot of control over the length of the data that gets transmitted because it's transmitted in a packet. And that was already predefined, and it didn't match the lengths that were needed by the Ctr DRBG. So they would have liked to have used the Ctr DRBG, but that didn't work for them. So they used the HMAC because it was tolerant to those different sizes, and they didn't use the hash because I told them not to, because they asked my input on what they should use. And I said, well, you could use HMAC or CTR. CTR is more efficient. And then they said, oh, but we have this problem with our data sizes. We want to use HMAC. So that's fine. Just don't use hash. So that's it. Well done. You've got through the whole of SP800-90A. If you are implementing random number generators, cryptographically secure random number generators, this is a place you can look to get them. In constructs which are probably okay as long as you avoid the hash DRBG. Definitely okay if you use the Ctr DRBG, and kind of definitely okay if you use the hash DRBG, subject to my concerns about the algorithmic connection between supposedly full entropy data. And that's it. In the next one, we're going to look at some non-NIST PRNGs, so like cha-cha-cha and some others. These have some other properties. They're more efficient or less efficient, things like that. But if you want something which is going to need to be for certification, the SP800-90 are the ones you're going to have to use. And so good luck. And I'll see you in the next talk.